As it goes closer to zero, it is extremely diverse. The area is extremely diverse. There's high diversity. And as you go closer to one, right, the diversity increases, the diversity decreases. Right? Normally we use two values, 1 minus d or 1 over d to show the diversity. You'll understand that when I go to the next slide. All right, so this is an example using the same figures that we used in our last class. Remember 0.167, 0. The three areas, green art, purple art, and Wallaber. However, this is what we're doing now, right? We're summing up the values squared. Somebody for just our academic performance, could you square these numbers for me? Let's see what we're getting. What are we getting for 0.167?
1 second, sir. The phone giving me some time here. 0.167.
I normally buy phone for
0.167
students.
squared.
You heard me? I normally buy phone for students.
Oh, no, it's okay. It's just because my hands were wet because I washed my hand and I touched the screen.
Yes, tell me. Yes, tell me. What are we getting here?
167.
Squared. What am I getting here?
0.027.
All right. 0.028, I think.
Yeah, 8.
Yeah.
8. I rounded
Rounded
it
up.
back.
Yeah.
All right. The next one is 0.333. 0.111.
1. That's good.
Mm-hmm. The
Plus.
last one is 0.5.
All right, that should be easy.
It is
Yeah.
0.25.
Good. So, and when we add here now, what we get?
0.25 plus 0.028 plus 0.111. 0.389.
All right, equal to 0. We're lucky this time. 0.389. Good. So we want to know now what is the diversity. All right. We got a value for D, but in terms of diversity, remember what we're saying here. We're using these two. We use this to determine diversity, 1 minus D or 1 over D. All right, so let's see what we're getting here. So this is 1 minus D, which is the same as 1 minus 0.028. 389, which would give us
Yes, sir.
0.6.
The 0.611.
11. Great. But remember, we said of our range, right, is from between 1 and 0. Let's put it the other way, 0 to 1, with 1 having the low diversity. Right, and 0 high diversity. Good. So this one is closer to what? Closer to 1 or closer to 0?
Closer to 1?
Closer to 1. Right? So it's
Still,
not so much, yeah, and it's borderline, because I think it might be 0.5 that separates 1 from 0. So it's a little over the middle. So they consider it moderate diversity. Right? They consider it moderate diversity. So once you know how we arrive there, let's save this here. This explains something here. Now, the Shannon index emphasizes richness, right? And the Simpson's index emphasizes dominance, right? They both complement each other. Let's see what the Shannon index emphasizes richness. So Shannon index focuses on capturing the most rare species. If it's there, Shannon index would account for it. Now, how is this interpreted? High Shannon values means that the community may have many species and their abundances fairly even. Right? The Shannon index accounts for and gives more weight for rare species, because every rare species that is detected, the index goes up. Right? And this index is used when you really want to measure all overall diversity. And you want to compare two systems, you want to compare two ecosystems, as I will show you just now. You want to compare two ecosystems, you're not too sure what is going on. The Shannon index fine tunes and says this one here is right more diverse than the other one. In this a little video I have for y'all, not prepared. I took off the net for y'all. You'll get a feel for what's happening when you have similarly looking environments. Right? So they say an example here, two forest sites may have similar total number of trees. The number of trees might be the same, but one has one more species. Right? The one has one more species, the Shannon index will go up and indicate that that area has a higher diversity index. On the other hand, The Simpsons Index focuses on the most common species, the dominant species. The word gives you a diversity index. It focuses on the dominance. Now, a high Simpson index, this is the interpretation. A high Simpson index is considered to have low diversity. And once it has low diversity, it means that a few species, of one or a few species, dominate. Right? So when you have a high Simpson's index, right, it can be interpreted to mean that you have low diversity and the area is dominated by one or a few species. Now, a low Simpson index Are you guys still with me? The internet did a little dance just now.
Sir,
Are you
you're
still
still with
there?
us, but we can't see your screen anymore.
All right, yeah, well, I need to put back the screen there. Yes. So this system is good for detecting dominance patterns. Stand. Right? So if you go in the river and yes, you still may have the 3 species or 4 species existing. But here is where in river, the dominant species is Rhizophora mango. If you come out on the coast, the black mangrove, Avicennia germinans, dominates. Right? So when you're checking on biodiversity in an area, it may be useful to use both indices, right? Because one would tell you that there is some amount of diversity, but the other one would flesh out and tell you if one or a few species are dominant. But I want you to remember the interpretation of the Simpson index. A high Simpson index means that there are few species that dominate. And a low Simpson index means that there is high diversity and there is no one species that dominate. Just remember that. All right. For example, here they give you an example of Rhizophora mango. Covers about 80% of an area in a river. Right. The other species are sparse. So the Simpson's index will show high dominance. Right. Reflected as low diversity. Right. Once you get a low diversity, and once that Simpson index goes closer to 1, and it will grow for Rhizophora mango, it will go closer to 1, you can know that the diversity is low, but it means that a few species dominating, in this case, Rhizophora mango. All right, let me go back. I just want to go back to the interpretation. With the Shannon, the values mean that the community has many species and their abundances are fairly even. If there are high values, right? If the diversity is high in the Shannon, when you get a high diversity index, it means that the community has many species and their abundances are fairly evenly distributed among the species. It also gives more weight to rare species because it is able to detect rare species, right? Because it increases the number of species present, right? It can pick up that. As against the Simpson's index, right? That can tell you a high Simpson index means that few species dominate. A low Simpson index means that no species dominate, right? And the diversity is as such. And this is an example of the indices we have for our forests generally, right? This is for that H represents what? Like people gone out, man. The H represents what? H represents the Shannon value. The 1 minus D represents the Simpson's value. They're just comparing it. So look what's happening here. The Shannon says the diversity is very high, right? What Simpson says here. Something is happening here closer to 1. Something is dominating. Something is not, excuse me. Something is happening here. 1 diversity low, 0.1 diversity low. When the diversity is low, what happens? Simpson. No one species dominate. Right, and these are figures that were generated from sampling the secondary forest. No one species dominates. No one species dominate. They're fairly high because biodiversity, the diversity is high. All right. Richness versus evenness relationship both affect total diversity. Right? Remember what we said. If you have species that have, if you have similar number of species and one has a more even distribution in terms of the abundance, that one has a higher diversity than the other one, which has lopsided abundances. Richness with low evenness gives moderate diversity. Richness with low evenness, meaning you have not quite the distribution, the even distribution as you would like. Right? There's variation in the distribution. Once the richness is high and the evenness is low, we consider that to have moderate diversity. All right. So these things are used for assessing like logging impacts and restoration success. Right? After you have logged, before you log, you could have taken your data after you logged, you could have taken a follow-up measurement, and you can use the Simpsons and the Shannon index, right, to do your assessment. It helps in monitoring. I think we spoke of that earlier, right? It helps in tracking changes in forest composition over time, both in the seas. And there's a study of mangrove restoration in Guyana. Before, two species had a Shannon diversity of 0.8. That tells you nothing. But after 5 years, you encountered 4 species. Shannon index went up to 1.6. Now you can use this information to say that there has been some improvement in the vegetation over a 5-year period because there was an increase in diversity. What caused the increase, we don't know. Right? You need to investigate. Right? And they say it indicates ecological recovery. It means that something is happening positively to the environment. Right? Suppose you when you went back, right, you saw the same species, you saw the same 2 species, right? But you got 0.7. It means that the 2 species actively happening because the Shannon index says there's a decrease in diversity. Right? Possibly one species outcompeting the other. Another example here, half-acre plot monitored yearly. Half-hectare plot monitored yearly in Iwokrama. It's stable because the age value shows, a stable age value shows that sustainable forest management is in place. Right? So if you when you monitor this plot here, and you come back and you get almost similar figures, similar age values, right? It shows that if the age value is stable, it shows that there is sustainable forest management. It means there is no serious destruction of your environment, right? So if you have similar values, right, you measure it from year to year, well, this year, and let's say you measure it for 5 years continually, and you have similar Shannon values, you could safely say that nothing is being destroyed. There's no negative impact, right? And there possibly a sustainable forest management. All right, and this is an exercise that possibly you give you all later to collect species data from the field sites. Possibly have a go at this when we go up to Rupununi, and we quickly calculate the H values and the D for comparison. Tools. Yeah, we don't need Excel and R. That's if you have extensive calculations to do. These are statistical tools. And we could have discussion on what you found and so on. All right, key takeaways from Shannon and Simpson. Shannon addresses the uncertainty and richness of the area. The uncertainty that 2 individuals selected from an area will be different. That's what the Shannon assumption it makes. Simpson, on the other hand, is saying two individuals selected from this area may be similar, right? Because it emphasizes dominance and evenness, right? So if you find the area, the species is dominant, as in what Simpson would try to tell you that these two species, this particular species is dominant, because if you go randomly and you select two species, most likely because of its dominance, you're going to select two dissimilar species, two individuals of the same species. However, these two assessments should be taken together, and it will give an idea of dominance, diversity, evenness, and give you the whole output. All right, we'll have a go at that, and we'll see what happens. All right, so much for this here. I have two small, interesting videos for you. All right. Where are we? Where are we? Come on, you. Is this the first one? Just a second. Stop here. How to measure? Not that one yet. That's doing by diversity. Let's see this here. Listen to that.
Hello.
All right. Are you hearing there? Loud and clear from what I just
Yes, sir.
put up?
We can hear.
Good.
Yes, sir.
All right. Here we
Well,
go.
learn how to do Shannon diversity calculation.
Start from there now.
Hello. Here we use Shannon diversity calculations based on total counts and percent. Now, if you were to ask anybody how diversity is defined, they would most likely tell you it's the number of species you might see in a community. Number of species, also known as species richness, however, is not a really good measure of diversity. Here we see two plant communities that have the same richness, the same number of species. But look at them carefully. Are they really the same? Hopefully you see that community 1 is in fact more diverse than community 2. Community 2 is dominated by one species in particular. So, even though both communities have the same richness, they do not have the same evenness or relative abundance of species. Community 1 is more even, and thus it is likely more diverse. Here is the equation for calculating the Shannon linear index. The value for diversity is represented by the letter H. H equals minus the sum of the proportion of species I times the natural log of species I. Here, I represents each species in the community, and S represents the total number of species in the community. So, to determine the diversity value for a community, we need to know the number of species as well as the proportion of each species. Proportions of species can be determined from total biomass, counts of each species, or the percent cover of each species. For biomass, if you know the biomass of one species, you can take that over the total biomass of that community to come up with the proportion for that species. Similarly, for counts, if you know how many of that species there are, or the total number of individuals in that community, you can get a proportion based on counts. Percent cover is a little easier because percents are essentially proportions themselves. Let's do a diversity calculation based on counts. In community 1, you can see that there are 16 total individuals. There is also 4 different species. In this community, there happens to be 4 individuals of each species. So, for the proportion of each species, it's simply the number of individuals of that species, 4, over the total number of individuals, 16, or 25%, 0.25. Here we have a highly even community. All species are equal in abundance. All 4 species have proportions of 0.25. So, to do the calculation for diversity, you have to insert the proportions of each species into this equation. Pi represents the portion. So, 0.25 times the natural log, 0.25 for species 1, and repeat again for all the other species. If you sum this up, you will get negative 1.39. Change the sign of that to get a positive value for diversity, and diversity for this plot is 1.39. Let's do this again for community 2. Again, we have 16 individuals. However, the number of individuals per species is a little bit different. For the first species, there is 1 individual out of 16. So 1 over 16 is equal to the proportion of 0.06. For the second species, there are 2 individuals out of 16. So 2 over 16 is equivalent to the proportion of 0.12. For species 3, there are 11 individuals out of 16. 11 over 15 is equivalent to the proportion of 0.7. And lastly, for species 4, there are 2 individuals out of 16. Once again, 2 over 16 equals 0.42. Based on total counts, we now have the proportions for every individual species. We plug these proportions into the equation, and we calculate an index of 1.06. Let's compare our communities based on the values we calculated. For community 1, we calculated an index of 1.39. For community 2, we calculated an index of 1.06. Based on these values, we can see that community 1 has higher diversity than community 2. So again, to emphasize, although both communities have the same number of species, the same species richness, they are actually different in diversity because community 1 has more evenness. Let's do an example of the calculation of diversity based on percent cover. Many plant ecologists use quadrat sampling to estimate plant community diversity. They place a quadrat on the ground and by eye estimate the percentage of cover of each species. Now this might seem tricky. How do you come up with numbers for each percentage? A trick I like to do is to divide the quadrat into 4 quarters or 25 percentiles in my mind. Here's the quadrant divided in half. Here it is divided in quarters. Now, if the species fills one of these squares, then you can say it has 25% cover. If it fills two, then it's 50%. If it fills half a square, then you would say it's 12.5%. Percent cover is a little subjective. So if you're doing a study where you're comparing sites, it's best that the same person is coming up with the values at each site. Each person might have a bias in terms of what percent coverage looks like. When I do this work in the field, often I'm in a group and we will come to a group consensus on what the values are.
All right, this is very important.
Yes,
If
sir.
if one person is doing the measurement, let that one person continue with the measurement, right? Because I might estimate one of the quadrants to be, let's say, 39% filled. Another one will say, is 50. Another one will say, all right, it's 49, right? But if that one person is doing that all the time, the error is consistent throughout, and there's not fluctuation. So it's very important. We can talk about quadrant sampling, and so the other video will talk a little bit about quadrant sampling. But the important point that he's making here, whoever starts the survey completes the survey, right? In order to minimize skewing and inconsistency and so on, right? Good.
So let's estimate percent cover for the species here. A quick look, and I recognize 5 different species. One species that fills up 1/2 to the left, and another grassy species that fills up most of what's on. Here we have a 3rd species, which is also found here. Here's a 4th species, and here's a 5th species. So we can assign the first species that fills the 2 squares on the left 50% cover. The grassy species, let's say it covers about 55% because it fills up plus 80. The 3rd species, found in this oval, we can estimate to be about 10%. The 4th, about 3%. And the last one, about 2%. As I mentioned before, percent cover is nice to use because percentages are already proportions. Here we have the proportions of all 5 species observed in the pond. You'll notice that all 5 species, when their proportions are added together, it equals 1. This makes sense because the plants covered 100% of the plot. If we take these proportions and plug them into the Shawinigan diversity equation, make sure you have every species represented. A little plug and chug, and the diversity calculation results in a 1 big index value for this plot. So what do you do if the plants in the community don't occupy the whole space? In other words, you don't have 100% coverage. Well, you still want to estimate the percent cover of each species. Here, we see 4 different species. First, a grass, which covers about 25% of the plot. Next, an herb, which covers about 10%. A 3rd species, which is only found in 1 spot, covering 1%. And a 4th species, which also covers 1%. Now again, this does not cover the whole plot. If you were to add up these percentages together, only 37% of the plot is covered. Now this makes sense because it looks like a lot of the plot is uncovered, roughly 63%. These percentages, however, do not actually represent the proportion of the individuals in the community community inside this cooperative. We will have to adjust those values. The way we adjust those values is taking the percentages of each individual over the total percentage of ground cover. So for species one, we take that 25 over the 37% that was total coverage. We now have a proportion of 0.6. You can do this for species two.
All right, I hope you're following here now. What they did to come up with that 37, they're saying that the vegetation that covered ground covered 37% of the ground. The rest that was bare, they did not account for that. All right, they were just looking at what the vegetation covered because they want to get that 100% that they're looking for. Right, so they're saying 25% of the entire area, which is 37, well, what we call 37 of the coverage. Then 10% of the 37 was covered by this species. Then 1% of the 37% was covered by the ape, and then another 1%. So what they're looking at is percentage cover, right? If normally if the entire place was covered, 100%, but it's only 37% was covered by vegetation. Right? So you're breaking that 25 of the 37 was covered by, so that's 67%, 10%. And then you will see how they arrive at the, when you add up these figures, you would get 1. Right? But they're just making proportion of the coverage. This is a tricky one. Not really recommended. We prefer the counting in we prefer the number count, but there are cases where you have to use percentage cover. Right? So there's a way out in also measuring this.
3 and 4, each calculating its own proportion. Again, here, the denominator is 37 because there was 37 covered upfronts in the corner. You know you've calculated the proportions correct when they sum up to 100 or 1. When you have the correct proportion, you can now enter them into the equation to do the calculation. Here we see that the diversity of this plot, even though the ground was bare, was 0.83. It's important to note here that bare ground does not mean a decrease in diversity. You can have a lot of bare ground, but if you have a lot of species and they're evenly distributed, the diversity can still be. The diversity calculated here is low because certain species that we found had very little cover. The proportions were not very good. This concludes our discussion about how to calculate the Shannon-Wiener diversity index. Next.
All right, I will share this with you that you can go over and over and over and get an understanding of what it is. All right. Right.
Hello, this is Dr. Acton from Mountain Science, and this is called we are going to do investigation and to estimate the population size of daisies in our field. To do this, you'll need quadrants and we'll need to know the area of your field. I've measured the length and width of the field using a drum number, approximating into a rectangle. Multiplying those gives me a total area of 620 meters squared. Yearly, what you want to do is to split this area into a 1 meter squared, for which every square in the top line being 3120. Then use a random number generator to choose random coordinates for your quadrat. This removes any bias.
All right, so they can use a random number generator. If you're not familiar with that, it's a computerized system. You just ask the system to generate random numbers, and you choose and you give it from one to how many, and it will generate random numbers. Say, look, I want you to generate 10 random numbers, and it generates it. However, when you're in the field and you measure off your area, you can use those you could have a quadrat. Let's say a one by one quadrat, right? Direction. Or you could ask your friend, what direction do you want me to throw this quadrat? So pitch it wherever it lands. You mark off that area. That is one area that you would mark. What you're doing is you're randomizing your selection. All right, so there are many tricks in the field that you go out to get your random squares to measure. All right, but this guy is using, he's just generating it. He has put this area on a grid and says, these are the areas. Then he goes on the ground and he marks all these areas. Those are the areas he's going to measure. Right, but there are many things you can do in the field. And when you go in the field, I'll show you how you can use your quadrats to do almost any assessment. Good.
To be accurate, shares a sample about 5 to 10% of the total.
Let's go back slightly there.
Random generators choose random coordinates for your quadrat. This removes any bias. To be accurate, shares a sample about 5 to 10% of the total area. So for example, 30%.
Importantly, know your sample percentage. He's sampling 5 to 10%. If your area is large, you can't go for 50%, you can't go for 100%, you can't even go for 30%, right? But he is choosing 10%, but you need to know your sample size because you want it to be representative of what it is you're measuring.
I'm just going to use 10 today. You then place your quadrat at those positions.
So when you add up the spaces that these quadrats occupy, right, it's a 10%.
The number that shows values. But in our case, these are unique instances of flower, daisies, asparagus. So once your quadrat is positioned, you need to count the organisms, in this case, daisies, with 1 meter square. 1, 2, 3, 4, 5. This one here is on the edge of the quadrat. But because over half of the flower is within the quadrat or underneath the quadrat itself, we will count that flower. So that means there are 6 flowers in this quadrat. We would not count this daisy here because it is not over half in the quadrat, so it does not count.
Right, so he has his protocol for deciding what is in and what is out. If half of the whatever plant or flower or what have you, right? If more than half is outside of the quadrat, this is not counted, right? If more than half is under and in the quadrat, it is counted.
Even if it is partially covered by the quadrat, it does not count unless at least half of that organism is within our 1 meter squared. Here are my results. What I then need to do is find the mean average of daisies per metre squared. For me, this is 7 daisies per metre squared. To estimate the total population, I just need to multiply this number by the total number of metres squared in the field, 620. This gives me 4,340 daisies. You can use this method of random sampling to compare population sizes, or even repeat this in the same area at different times. However, there is another way of using a quadrat that allows you to observe how population density varies between certain points within an area. For this, we are going to use a transect quadrant. First thing I need to do is lay a measure along the area going to be sampling. I lay this one out to a distance of 10 meters. And then with a sample along this line at 1 meter intervals and the number of organisms, record those results. So place the quadrant at the start of my transect, and I can see that there is 1 daisy on the edge of my quadrant here. So I'll record that in my table. I then need to move the quadrant up the transect 1 meter at a time and count the daisies each time. Here are my results.
All right, just kindly note that he's using 10 sample points again because he wants to maintain that 10%. All right, there are different types of transects, and he could have done an intermittent measurement where he stretches the tape further in, let's say to 20, and he measures every other meter. Right, but you want to get those 10 inside. Right, so many different forms of trans. This is a simple one. We need to understand this principle first before we move on to the others.
I plotted a line graph to show the population density changes at distance from the line. I plotted a line graph to show the population.
All right, this is what he did.
Here are my results.
So he has 2 different sets of information, and he can plot a line graph now. X-axis, Y-axis, and you plot 0 against 1, 1 against 1, 2 against 1, 3 against 1, 4 against 5 against 4, right? And he will generate a pattern. He wants to see if there's a pattern.
I plotted a line graph to show the population density changes at distance from the lines. I can also use a you can see the number of densities from the square increases at the yeah.
All right, this is a positive graph because it keeps going up. Right, so the population increases, the distance increases. As the distance increases, the population increases. And here is the pronouncement that he's going to make. And this is how important just a simple assessment could be.
Use a time.
Good.
As you can see, the number of daisies per meter square increases the further the number they are. It's like the cause of this is people travel as they walk through it. Pattern which increases with distance from it. This is what we call a biotic factor, as it is due to living organisms. Abiotic factors are those that are not due to living things. For example, light intensity or pH of the soil.
Good. Wonderful. Let me see this. Yes, so that's just to whet your appetite with transects and quadrats. Right, the information that you get from transects and quadrats, you could input it into your Shannon calculation, you could put it into your Simpson calculation. Good. I'll stop here for today, but I'll give you some homework to do in doing some calculations with Shannon and Simpson. Simple calculations worth about 5%, but I want to know if you grasp what you were taught. I will put it on Moodle, right? And you do it and send it to me next week, Thursday. And when we meet, based on what I see, we will further discuss these two calculations of diversity. Right? So
Yes,
I
sir.
leave you here.
Um,
And why I'm leaving you here, I have timetabling issues. I have another class starting shortly but I now started teaching it because somebody else would have finished their part of it. So I have one shortly at 3:15, so I need to go on to that. Not shortchanging you, but I will put up those assignments so you can do your work. Now, I hope that everybody has submitted their assignments and report. My best guess of what I saw, I think everybody would have. Right? So we're going smoothly so far. Today's Thursday. I made the out of circulation on the 30th of this month. Right? But I'll tell you that on Wednesday when we meet. Right? So just keep that in mind for now. But I will tell you.
excuse me, sir.
Yes,
Just before
yes,
you
Amit.
go, other than the mosquito net with the hammock with the mosquito net, is there anything else that we would need for the Latam trip? So just in case we need to buy it or so?
Insect repellent,
Mm-hmm.
very useful.
Okay.
Insect repellent. If you have a small blanket, might be useful because it will be a little chilly in the night. And hammocks.
Okay,
Hammocks,
sir.
water bottle, right? I will send a list of things that I want y'all to walk with. I'll put it on Moodle, so you have an idea of what it is you should walk with.
Okay, sir. And the
Not
other thing quickly is that are we leaving like Friday morning or Friday night? Because and same thing for Monday. What time would we be coming back? Because we might have to tell our lecturers that we won't be able
all
to
right.
attend online class just in case.
So what we're trying to do is to leave here Thursday evening, so you don't have classes Thursday evening and try to get back here Sunday evening by 6 o'clock or so.
Okay, sir. So it's from
Right?
Thursday.
Yeah,
All right.
from Thursday evening, we can go there. We can stop at the crossing. We can spend the night at the crossing. Everybody, please walk with a hammock and rope. Right? We doing the heavy lifting now. Walk with hammock and rope because we're gonna spend the night at the crossing. Early in the morning, we have breakfast and we head over straight to Iowa Kramer, and after then we make several stops along the way, and then we overnight where it is comfortable to sleep in a village. Right, and then the next day we have a full day, Saturday, And then I think we may stop at the Iwokrama field station on our way out on Sunday. To just have a look and see. Many persons have not gone to Iwokrama, so we take the opportunity to just drop by. In fact, possibly have a lecture there. And then we should be leaving by 1 o'clock to head out back. So by 6:30, we should be in town. All right, try to avoid the night thing on the highway too.
Okay, sir. Thank you.
But I'll give you all more details as we get closer to the date. All right, but
Okay,
check
sir.
check Moodle, and I will set up everything that you need to work with. It is not anything that you need to go and expense yourself. Basic stuff.
Okay, sir.
All right, you're welcome. All right, see you when I see you, folks.
Bye, sir. Enjoy the rest of your day.
You too. Bye.